Are there any questions?
Yes.
Yep.
Yeah, sure.
Chapter. 54, okay. All right, so the question about number 54 from chapter 8, this is the long stick with a mass hanging on the end of it. The torque needed. So I guess one is up like this with the mass hanging down. One is like this with the mass hanging down. And one is like that.
Yeah.
Well, let's take a look at the extreme. If it's like this, if the meter stick is straight up with the mass hanging down, that's not much better. With the mass hanging down, then I'm just basically balancing it. There's no torque is required at all because there's no, assuming it's perfectly vertical, there's no desire for it to swing one way or the other. So if it's perfectly in line, there's not going to be any torque. So the farther you get away from being perfectly in line, the less torque needed. So the question is, how far out does it go? Well, the one that's like that is going to be the most torque.
Okay.
And then, can't remember, in the picture that they had, this one would be the next because it's the next farthest out. And then the closest one to vertical would be A.
Okay.
So from largest to smallest, so it would be BCA. Not, did you need more?
No, I'm just
Okay.
trying to look at my notes.
Other questions?
84. And what did-
Friction is needed for a car rounding a curve?
Yes.
That one? Okay. But if the road is banked, friction may not be required at all. What then supplies the needed centripetal force? So start out with the car on the flat surface. Rear view. And then overhead view, something like that. Which way does the car want to travel? If this were ice, which way would the car go? Car going around the curve that way.
Sorry, that way then.
Okay, so it's going to be, it wants to travel in a straight line. So something's got to be, since it's not traveling in a straight line, the velocity changes, therefore there must be some net force acting on it. So in a frictionless situation, it goes this way, so friction must be acting towards the center of the circle. That's the centripetal force. If we put it on a bank, so back over here, if we look at do a force diagram, we have weight acting down, we have normal force acting up, and we have friction acting towards the middle. So as long as I get some force acting towards the middle, that potentially could be enough for my centripetal force. So if we put it on a banked curve, still overhead looking like this, what are the forces acting on the car? Looked like you were about to say it, Chase.
Yeah, weight going down,
Yep, weight going down.
friction going, I guess,
We're gonna assume no friction at the moment.
okay. Then, normal force going the other way.
Going,
Or going.
yeah, there we go.
diagonal.
So the question is, looking at this, is there any part of either of these forces acting towards the center of the circle? So the other question is, in which direction is the center of the circle? If you're going around a curve like this, where's the center of the circle? Which way?
In between the weight and normal force.
Okay, closer to normal force than the weight, but in that direction.
Yeah.
So the question is there any force that has a component in that direction? Does weight have any part of it in going that way? Does normal force have any part that's going that way?
I mean,
Yeah, part of it is. Part of normal force is going to the left, and part of it's going up. Well, the part that's going up is countering weight. The part that's going to the left is making it travel in a circle. So you don't necessarily need friction in order for it to. There is an ideal speed at which you can take a frictionless curve and not fall off. That's because part of the normal force is the centrifugal force. Follow-up questions to this? Other questions?
would you come on over 116 in chapter 8?
Problem 116. Most often we say that the force causes acceleration. But when Evan took a ride in a rocket sled on the bottom full of salt flats, blood was forced to the back of his brain, nearly blacking him out. Discuss and identify the cause of this force. Well, I'm open to suggestions. What would cause the brain to move to the back of his head? I'm not 100% sure why this is a chapter 8 problem, but it's more like a chapter 2 problem. What's Newton's first law of motion?
Object in motion stays in motion.
And then,
Unless force acts upon it.
right, or an object at rest stays at rest unless an outside force acts on it. So the blood is here and he's accelerating that way. His blood, actually his brain, everything wants to stay where it was. If he's going to accelerate in that direction, then there has to be something pushing him, and everything just wants to stay doing whatever it's doing. And so what happens is if you've got, the skull, you push on the back of the skull, the front of the skull is going to move. But the squishy stuff inside requires it basically you get pushed to the back in order for it to get pushed forward. So if I have a gas molecule here, and I know gas versus liquid, but if I have a gas molecule here, it's not going to move until my hand actually gets to it or gets close to it. Similar to liquids, somewhere between the liquid and the solid. But if I push on if I push on this end of the table, that end of the table is going to move pretty quickly. If I push on, I'm in a swimming pool and I push on one side, that force is not going to automatically be transmitted throughout the entire pool. It's going to take some time to get there. So the blood here, as I'm accelerating that way, the blood here, it's going to take a bit for it to start getting forced forward. So it's going to sort of stay as I come forward. Yeah, blood force. So blood was not really forced to the back of the brain. It was more like the back of his brain was forced to the blood.
So it's more like the inertia?
Yes,
Okay.
very much.
What question was that you were doing? Like,
That one was 84.
Okay, could you do 79 in chapter 8?
79. All right, this is a torque problem. So if I just have, we'll just imagine a very thin rod. If it's perfectly balanced right here, perfectly vertical, and the gravitational force is down, no error, nothing to worry about that, it's gonna stay balanced. If it tips, if it's slightly bent in that direction, well, you think about the center of mass, because we can treat the center of mass as sort of the location of any, of the weight acting there, unless you want to get into some civil engineering stuff, which we don't. So the center, as long as the center of mass is over the balance point, it should stay balanced. If the center of mass is not, then my weight is acting there. There's my axis of symmetry, or axis of rotation, and so now I have a torque acting. If I have a torque acting on it, then I will have angular acceleration, which means it's going to start to tip. In this particular case right here, where it's perfectly lined up, my weight is acting straight down. There is no torque because the weight is going right towards the pivot point. So like pushing on the end of the door trying to open it, if you're pushing straight towards the hinge, it's not going to do much. So in this particular problem, we're looking at where are we going to have a torque or not? So if I've got wheels here, if the center of mass is there, then if that's my axis, because if it tips over, it's going to tip over on this part of the vehicle. There's my axis of rotation. If the weight is on that side of it, it would cause torque, therefore angular acceleration, it would tip over. If it's over here, well, I have this force right here acting against it, so I'm going to have torque from the truck itself, but I'll also have torque from this normal force here. And so they can balance each other out. So as long as the center of mass is, given the way I've drawn it, to the right of this corner point right here, it won't tip over. Is that sufficient?
Yeah,
Okay.
thank you.
Other questions?
Can you go over 34 in chapter 9?
Chapter 9.
Yeah, because I got 2.443 newtons, and then I did the formula, and you have 2.5.
That could so easily be rounding. Which problem did you say again?
34.
Calculate the force of gravity on the 1 kilogram mass if it were 6.4 times 10 to the 6 meters above the Earth's surface. So I think in class I used 6.38 instead of 6.4.
Okay.
So
Yeah.
that could be enough to make that difference.
Okay.
Of course, what would have been printed as far as the solution would have been the book solution, so.
Yeah, for some reason I calculated 2.443 newtons, and I just couldn't figure out. And I kept checking to make sure I didn't miss any numbers.
Yeah, I suspect it's just a rounding thing. You still want me to go over it, just to see if you set it up right? Okay.
Number 46 about the candles and the flames.
Consider the light of multiple candle flames, each of the same brightness. Rank the light that enters your eye from the brightest to the dimmest in the following situations. All right, so we have 3 candles, 2 candles, 1 candle. So it gives off a certain amount of photons. A light will give off a certain amount of photons. Photons is basically what carries the light. That's what's going to hit our eye. Our eyes will react to it. Oh, there's your. So 3 candles. From the same distance, 3 candles should be brighter than 2 candles, brighter than 1 candle. Matter of fact, 3 candles should be 3 times the brightness of 1 candle. So I've got 1, 2, and 3. Now the other part of this equation is the distance. So this goes out, this one goes out, and it'll start to spread out. The farther out it goes, the dimmer it should be. This one will also fade the farther you get. All of them will. So if I am lost it there. Okay, so 3 candles from 3 meters. So if I'm 3 meters out, that 3 brightnesses get spread out over a sphere. And the sphere is proportional to that distance squared. So the brightness will be 3, but it's also spread out over a larger distance, so 3 over 3 squared, which is 1/3. This one would be twice the brightness, but spread out over, I guess, goes out to sphere size 2 meters. So that would be 1/2. And then the 1 candle over 1 meter would be the brightest of them all, in terms of what hit your eye.
That was 46.
Yes, that was 46.
And then 47, I just felt like I don't know why, but I thought the speed at the center was 0. Remember letter B, but it's not, it's just, that's the fastest it will be.
Yeah, acceleration is 0.
Okay,
Because at the center, you are being basically pulled in every direction equally.
okay, that's what I misunderstood.
Okay.
The acceleration is 0. But the speed is the fastest it'll be is at B.
Right.
And then the slowest, the speed will be is at D, because it's
Yeah, that's when you pop up on the other side before you
start
get
coming
sent.
back.
Yes.
And, okay,
In the absence of air resistance, it's an energy problem. The closer you are to this, you basically keep losing potential energy and gaining kinetic energy. The closer you get to the center, then once you pass the center, you'll start gaining potential energy and losing kinetic energy. And in this particular case, in a nice ideal situation here, it's simple harmonic motion, which we'll get to in chapter 19, and it'll just oscillate back and forth.
yeah, that's what I thought it was gonna do, was we just go back and forth, that's what I was going for.
Yep, similar to, well, if you took a slinky and pulled it down and let it go.
Like a bungee cord.
Yep. Other questions?
Could you go over number 60?
So chapter 9, number 60, an astronaut lands on a planet that has twice the mass of Earth and twice the diameter. How is his weight different? First off, his mass is the same. All right, I know that the force due to gravity, the magnitude, is going to be this constant times the mass of the astronaut times the mass of the planet divided by the radius of the planet squared. And so if we're talking about Earth, that's just going to be big G, mass of the astronaut, mass of Earth, over the radius of the Earth squared. This would be his weight. Now we have a short, if he's standing near the surface of the Earth, well, I'm assuming that he's standing on the Earth, then we just generally use in little g and be done with it. But this is, you can do it this way. So this is the weight on Earth. Now the weight on the planet, it has twice the mass and twice the
Yeah, radius,
twice the radius, twice the mass.
yeah,
So twice the mass, so big G, mass of astronaut, times 2 times the mass, 2 Earth masses, over, well, twice the radius, 2 Earth radii squared, which is just, well, on top I've got a 2, then big G, M, A, N, E. And on the bottom, the 2 gets squared also, 4, R, E squared. And so it's going to be 1/2 of what it was on Earth. Very,
I see where
very
I
similar
messed
to
up.
this right here.
yeah, I see where I messed up, I didn't square the 2,
That would do it.
yeah, I'm like, wouldn't it be the same?
If the radius were 40% more than that of Earth, that would be the same. 41 point something. questions?
Can you explain 111, for chapter 8?
Chapter 8, problem 111. Eventually. The obnoxious boy and the seesaw. Is that a problem?
Yeah.
If we do a normal seesaw right here, if I just, it's perfectly uniform distribution of board, and I've got a pivot point right there, I can treat this as two parts. I got half of it pulling down there, half of it pulling down here. They exert the same torque. I have force with some distance away. We'll just say 5 newtons, 3 meters, 3 meters, 5 newtons. They exert the same magnitude of torque, just opposite directions. This exerts a torque out of the board, this exerts a torque into the board. They cancel out. I could also look at this as I've got a board here with all of the weight acting right down smack dab in the center. And so therefore the weight is acting at that spot right there. It exerts no torque. It'll stay balanced. Either way of looking at it is completely valid. If the board is off balance, I can look at it from the point of view of I have the weight acting at the center of the board that's causing a clockwise torque or torque into the board so that this end would go down and it's going to go like that. Or I could look at it from the point of view of, well, this half of the board, I've got a force acting in its middle, not the middle of the board, but just the middle of this half. And I have a force acting down there. This has a shorter moment arm because that distance is shorter. It has less weight because that piece is smaller. This has more weight and a longer moment arm. This will have more torque that's going to rotate counterclockwise again, or sorry, clockwise again. Now, in order for this to be balanced though,